Hello world, my name is David Malan, and on behalf of the team that brought you CS50, we are here in the beautiful world of university theater, in which we're producing a brand new course on math for introductory computer science. In fact, a frequently asked question over the years has been, what math do I need to know in order to take CS50 or any introductory course in computer science? And FAQ has been, if I'm not a math person, can I do computer science? Can I learn how to program? And for years, our answer has emphatically been yes, but we didn't really have a course or a resource to point you to, but now we will. In fact, thanks to our friend Tom Crawford, professor at the University of Oxford, the University of Cambridge, and famously of the website tomrocksmaths.com, that's maths with an S, where you can find all of his socials, we'll be introducing you to all of the basic building blocks that will help you succeed in a course like CS50 in introductory computer science more generally. You'll find that some of the topics are probably familiar, even if you're a little bit hazy on them. Maybe you learned them in high school or grade school or somewhere along the way. And some of the topics might be brand new to you. And it's not meant to be an in-depth study of those same topics, but really a refresher of and an introduction to just enough math so that you can dive into a field that you might particularly want to explore, namely computer science, programming, AI, and beyond. As you'll see on the bottom of the screen, this is a behind-the-scenes film, which means that we'll be fixing things, changing things, starting and stopping. So this won't necessarily be the best educational experience. For that, wait till the final post-produced version of the course, which we'll announce before long. But if you'd like this sneak peek of the course, if you'd like to get to know Tom Crawford, if you'd like to get a sense of what's going into the making of the course, this is the live stream for you. We'll begin in just a bit.
Hello world and hello maths fans. Today we are going to be learning about numbers, and I guarantee there is a lot more to numbers than you might think. We will begin with the familiar. We will look at the counting numbers, the natural numbers to give them their mathematical name. We'll then extend that into the negative numbers, and the positive and negatives together will give us the integers. We'll then look to fill in some of those gaps with the rational numbers, which are numbers that can be written as fractions. Also the irrationals, which are the numbers that cannot be written as fractions. And those two groups together give us the reals. We also will need to look at decimal expansions. We will look at the properties of fractions. We'll talk about significant digits. We'll talk about converting between decimals and fractions. And finally, at the end, we will summarize by a classification of all of these different groupings of numbers. And we'll also introduce some types of number you have likely never heard of before, including algebraic numbers, transcendental numbers, and my personal favorite, computable numbers. So as I said, a lot more to it than you might think.
That's great, Tom. Thank you.
when given a particular number, it would be helpful to know what type of number we are working with. And for that, we're going to need some definitions. So again, we're going to start with the familiar, the classic counting numbers. And mathematically, we refer to these as the natural numbers. So we say that a natural number is any of the numbers beginning at 0 and then successively adding 1. So exactly as we would count objects. So 0, 1, 2, 3, continuing. I will just add a small disclaimer that not all definitions of the natural numbers include 0. Sometimes they are written without 0. But here I am going to use this particular definition. So 0 is indeed, as controversial as it may be to some of you, it is indeed a natural number for our purposes. We often refer to the natural numbers using this scripted letter n. Now, from the natural numbers, we then want to move into the negatives. And we actually generate the next collection of numbers, which we refer to as the integers, by adding in the negative version of our counting numbers. So we say the integers are the natural numbers, the counting numbers we've just talked about, plus their negative counterparts. So for every natural number, there is a negative counterpart, apart from 0, because of course negative 0 is still 0. And these are generated by simply writing a minus sign in front of all of those natural numbers. This collection of numbers, I would say z, some of you may say z, but that is the notation that you will see when talking about the integers. So now we have our positive whole numbers, counting numbers, negative whole numbers, together giving us the integers. There's still quite a lot of gaps between those numbers. And this is where we need the rationals. So the rational numbers are going to be our fractions, basically. So they are going to consist of a fraction where the numerator, the number on top, and the denominator, the number on the bottom, are both integers. Now these can be positive or negative. Remember, both of those are allowed in that collection of integers. So we've got some examples on the board. We've got a half, so 1 and 2 are both members of that collection of integers. We've got minus 3 divided by 2, so we can also, again, have that negative number in there as well. And another example there, famous one, 22 divided by 7. Now, with the rationals, there is one technical counterpoint, which is very important. We can never divide by 0. So that number on the bottom, the denominator, has to be non-zero. Otherwise, we basically break maths, and we would like to avoid doing that. The rationals, we use the letter Q to refer to this entire collection of the rational numbers. So we've now talked through 3 sort of quick-fire collections of numbers. And these actually have relationships between them. So I'm just going to head over to the board, and we're just going to explore those in a little bit more detail. So if we start again with the natural numbers, the counting numbers, we had numbers like 1, 2, 3, etc., carrying on. And then to get the integers, that kind of slightly larger collection, we then just added the minus sign. So there's clearly a relationship there between the natural numbers and the integers. So here we might say it's minus 1, 0, 1, 2, etc. And I'll add in minus 2 as well. So we can see that the integers, that kind of next step up, have come from the original natural numbers. And then the third collection that we talked about, the rationals, actually has a similar kind of relationship. So what I mean by that is we can take any number that is an integer, and if we just write 1 on the denominator, so if you just divide that number by 1, it doesn't change its value, but suddenly it now fits our definition of being a rational number. So again, if I take the list we have, I just do minus 2 divided by 1. So this is now a rational number. It is a fraction where we have a whole number, an integer on the top, and another integer on the bottom. And the same for minus 1. That will just be minus 1 divided by 1. I'll ignore 0 for now, but 1 divided by 1 and 2 divided by 1. So for any integer, we just write a 1 on the bottom, and suddenly it's now part of the collection of rationals. So the rationals also, of course, contain other values. And so what we're seeing with these first three collections of numbers is almost like an increase in their size. And we'll talk more about that later. Now, there's a couple of other sets or collections of numbers that we want to be sure about. So the next one, having moved on from the rationals, is going to be the collection of numbers called the irrationals. Now, the irrationals are the exact opposite, in a way, of the rational numbers. So the rational numbers are numbers that can be written as a fraction. So where you have an integer on the top and an integer on the bottom. The irrational numbers, by their very definition, are any numbers where you cannot do that. So we say they are numbers that cannot be written as a fraction. So if it's not a rational, it has to be an irrational. Now, taking these two collections together, so the rationals, anything that's written as a fraction, combined with any number that cannot be written as a fraction, actually gives us all of the numbers. And we call that collection the real numbers. So this is the entire number line. Any point on that number line can either be written as a fraction and is rational, or cannot be written as a fraction and is irrational. So the real numbers contain both of these, and we can also refer to them as any number that has a decimal expansion. And the way we talk about or refer to the reals is using this superscript, this scripted letter R. So that brings us to the end of this whistle-stop tour of the basic, let's say, collections of numbers. So we started with the counting numbers n for the naturals, the integers, z or z. We then saw the rationals, which are our fractions labeled q. And then everything together gives us the reals r, where if you're not a rational, you must be irrational. The system that we use to represent numbers is known as the decimal system. And that prefix, DEC, or dec, is actually the Latin term meaning 10, which gives us a very strong clue as to what is happening with this particular way that we represent numbers. So if we go over here and look at an example, we have the number 1,234.567. And in the way I have just read out that number, I've actually given us all a clue as to what is happening under the hood with these powers of 10. So I said 1,000, indicating there we have one lot of the thousands. 200, saying again we have two lots of the 100. So the thousands column, the hundreds column. Again, I said 30 rather than 310, but it is telling us that we have three tens, 4.567, and so on. Now, if we were to add those place values very explicitly beneath the numbers, then again we can see this pattern. So we'll start from the left. So we have the 1,000. Now this, the thousands, is actually a power of 10. It is 10 multiplied by itself 3 times. So 10 times 10 will give us 100, times another 10 gives us the 1,000. So this is saying multiply 10 by itself 3 times, gives us the thousands, and that is the placeholder value for this location. Next along, we have the hundreds. So again, 10 squared means 10 multiplied by itself, 10 times 10. There are 2 of them in total, and that gives us a 2 in the hundreds position. We then have the actual tens column, so we just have a single 10, and that's where we have the 3. So 3 tens we would call 30. 10 to the 0, so this is actually the units space. So 10 to the 0 is equal to 1. 1 represents the units, and that's giving us here 4 units. And then as we move past the decimal point, the pattern kind of flips. So we've gone thousands, hundreds, tens, then we have our units, and now we go tenths, hundredths, and thousands. And we could continue in either direction with higher powers of 10. So we would go 10,000s, 100,000s, millions, continuing up to the left. And similarly, we would go to 10,000ths, 100,000ths, etc., as we moved further and further past the decimal position. Now, in order to remember these names, and in particular to be able to understand what we mean by tenths, hundreds, and thousandths, I actually have a fancy way that I like to remember this, which I'll show you over here on the board. So the way I like to do this is using the number of digits in the non-decimal version of the number that I'm used to thinking about. So for example, if I'm working with tens, so then I would say to myself, well, tens is 10. That's the value that we have. And it has 2 digits. So this has 2 digits. So when I'm now working with tenths, then what that is telling me is I also, for the tenths, the fractional value, the decimal value, I need to also have 2 digits. So tenths, written as a decimal, is going to be 0.1. So again, we've got 2 digits total, just as we have 2 digits when writing out 10. So if we look at another example, let's look at thousands. So if I want to think about the number of digits when I'm working with the standard form of thousands, 1, 2, 3, 4. So we write out the number 1,000. There are 4 digits. So when I'm working with thousandths, and the place where I'm used to hearing, and I'm sure some of you may recognize hearing about thousandths, it's usually to do with times. So I'm a big Formula 1 fan, and often it's, such and such a racer got pole position by 2,000ths of a second, and that's what it's indicating here is how many decimal places they have actually won the race by. So thousandths is, again, we know that it has to have 4 digits because it's like the reflection of thousands. So those 4 digits means we're going to have 0 point, because again we have to count the 0 before the decimal place, 0.000 1, and that is going to represent thousands. Okay, now, oh, having issues with my stylus. Okay, which has thrown me. Okay, we were talking about, sorry, I'm going to do a pickup there. Do I go from a specific word?
Why don't you just wrap up the previous sentence, and then
Yeah.
we'll just fade you in, fade you out. Yep.
Okay. Where am I going next? Okay, so we've talked about that. Oh no, there's one more example. Okay, my bad. Okay. No, I think that's fine actually. All right, I'm going to put that there.
Last thing you said was 0.001, and that's going to represent thousands.
Okay, great.
And you were looking at camera.
And I was looking at camera. That's going to represent thousands. Okay. Now there is another way. Now when talking about placeholder values. Okay, there's an. Okay, cool. Right. Thank you. All right. 0.001, and that is going to represent 1,000th. Now, when talking about placeholder values in this way, talking about decimals, there is another common notation that we will see appear in many different places, which is referred to as scientific notation. In the UK, we call this standard form. I'll be honest, I don't know why. I prefer scientific notation. So scientific notation is just a way of expressing a number and making it really clear what power of 10 or what place we are working with in the decimal system. So the rules tell you that we want to write a number less than 10 multiplied by a power of 10. And it's very important to remember that that first number must always be smaller than 10. So here, for example, sorry, I thought I'd made a mistake. Can we just quickly check? It has to also be bigger than 1, doesn't it? The number for standard form. Sorry, my brain was just like, I've missed something from the definition there.
Oh, I'll check it, but no, this is all correct.
It is correct, but I think when you say must be written as a number less than 10, it also must be greater than 1.
Yeah, I think that's right.
I think I should. Should I quickly change that and just redo this section?
I think so, and I would just
Sorry.
pick up right where you.
Yeah. So this represents 1,000th. The other way, so this represents 1,000th. The other time that we can see these representations of numbers is using a specific notation, which is...
It sounded like thousand. Can you
Yep.
sound thousand? Can you really hit the TH?
Thousandths, yes. Okay.
And last time when you said tenths, I think you said it in the plural, which kind of helps.
Tenths,
This represents thousandths.
thousandths.
Not
Okay.
a big deal, but
Yeah, no, yeah, we might as well while I'm stood here. Yeah, so fine. Okay. Do I just go whenever?
Yeah, Tom, you're good to go anytime.
Okay, thank you. Right. And this would represent, and this represents, so this would represent 1,000th. No, okay, this represents, so this would be how we represent, so lost now. Okay. Blah, 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 blah. So I've talked through thousands, 4 digits, thousandths. This has 4 digits. Okay, so then for 1,000th, we have the 4 digits. So 0.001. Okay, thousandths have 4 digits. So 0.001 would represent 1,000th. The other time that we often see powers of 10 written out in this way is with a very specific notation, which is referred to as scientific notation. Now, in the UK, we actually call this standard form, but I do prefer the scientific notation words. Now, scientific notation is always written as a number between 1 and 10, and what these brackets are telling us is that the number can be greater than or equal to 1, so 1 is allowed, but the curly bracket is saying it must be strictly less than 10. So we pick this number, or we write out that number, and then we multiply by the power of 10. So this is why it's important to be able to be comfortable working with these different powers of 10. So if we look at some of these examples, the number 11, again, is not a number inside the allowed range. Right? It is larger than the number 10. So what we have to do is kind of divide by 10, and so we write that as 1.1 multiplied by 10 to the power 1. So this 10 to the power 1 is basically telling us how to shift the decimal place. So because it's 10 to the 1, it's saying we take the decimal place and just shift it one place to the right, and that gives us the number 11. And that would be 11 written in scientific notation. Now for the second example, 314. So again, we're going to pick our number between 1 and 10. So this time it will be 3.14. So what we've had to do there is shift the decimal place 2 positions. So therefore, we're multiplying by 10 to the power 2, which is the hundreds. Final example of a number smaller than 1. So here we have 0.123. Again, this is below 1, so it doesn't fit into our definition of scientific notation. So what we're going to have to do here is, again, shift the decimal place 1 to the right. So we're going to write that as 1.23. But now, because we're shifting it in the other direction, we're going to write that as times 10 to the minus 1, which is telling us to divide by 10, or representing tenths. Now, in this last example, what we've got here is a particular type of decimal, so 0.123. This is what we refer to as a terminating decimal. And it's important to be able to identify what type of decimal we're working with when we're trying to classify the type of number that we're working with. So a terminating decimal is simply one that ends. It is something that terminates. So our example there of 0.123 or 0.125. So it has 3 positions and then it stops. A non-terminating decimal, of course, as you might imagine, does not stop. So a non-terminating decimal is going to continue. It's actually going to go on forever, because if it didn't, then it would have a stopping point. So it must go on forever to be non-terminating. And the example here, 3.141592. And to indicate that this continues, I'm using the notation here of ... So that's telling us that this is going to carry on, and it's actually going to never stop, it giving us the non-terminating decimal. The other important example is something called a repeating decimal. So a repeating decimal is also non-terminating, which means it is going to continue to go on forever, but there is a repeating pattern. So the way that we denote this is often written with a bar over the part of the decimal that is going to repeat. So here we have 0.142857, and because there is a bar across all of those 6 digits, that's telling us that those 6 digits then repeat. So it would go 0.142857, and then again 142857, and again 142857, and that is going to continue forever. So we have the terminating ones that stop, non-terminating meaning they go on forever, and then the repeating decimals, again indicated by this notation with a bar. So that summarizes the basics that we need to know about decimal expansions and working with powers of 10. we begin with a warning from history on the importance of correct rounding and the use of significant digits. So our warning comes from the 1980s and the opening of the Vancouver Stock Exchange. And when the stock exchange was set up, there was a slight error made in the computation that was happening with the value of the index. And what had happened was, rather than rounding according to the final decimal place of the value, they were actually truncating. So they were chopping off that final digit. So what this means is a number like 500.129, which we would round up to 500.13, was actually being chopped off. We lose the 9, and that would become 500.12. On its own, not a huge problem. However, with the stock exchange, these values were being refreshed up to 3,000 times a day, so that small amount begins to compound. And in fact, after 22 months since the opening of the Vancouver Stock Exchange, the index had lost more than 50% of its value completely as a result of a rounding error and some bad maths. So we are going to go through how to do rounding in significant digits properly to make sure something like that never happens again. So for significant digits, when working with significant digits, there are 3 key rules that you have to follow. And as long as you keep these in mind, then you should be able to work out any problem involving significant digits. So the first rule is, when counting a specified number of significant digits, we begin counting at the first non-zero digit from the left. So we find the first one from the left that is non-zero, that is our first significant digit, and then we count from that point. We must remember to keep all placeholders, so we can't throw away positions in the number and lose those values. And finally, we must round correctly and appropriately. And so what that's going to mean is, if the final digit is a 0, 1, 2, 3, or 4, then we're going to round down. And if the final digit is a 5, 6, 7, 8, 9, then we're going to round up. So as long as you keep these 3 rules in mind, you hopefully will not make any errors. So let's go over and look at some examples of this in practice. So let's begin with a question about 2 significant digits. And let's suppose I have the number 121, and I'm interested in expressing this using 2 significant digits, and I will use the shorthand SD. So following our rules, we look for the first non-zero digit from the left, so that's going to be the 1. So we can say that this, keep that 1. And now for the second digit, we have a 2. And then the next one along, the 1, is where we have to do the rounding. So at the moment, our final digit is 1. It tells us to round down. So we're going to keep the 2, and then we must ensure that we retain that placeholder. So it is important that we started with a number that had 3 digits in total. So our final answer also has to have the same 3 digits to make sure that it still has the same placeholder value. So 121 to 2 significant digits, we're going to round down and get 120. Now, if you look at a slightly different example, let's take the number 129. And again, we will look at just doing 2 significant digits as above. So this is going to be very similar. We start counting from the left, so we're going to get the 1. But now we have a 2 followed by a 9. So following our rounding convention, that 9 is telling us to go up. So we go up to the next digit, which is going to be a 3. And as before, we must remember to keep the placeholder, so we put that 0 at the end. Now, of course, we can round to, or we can write to numbers with more than just 2 significant digits. So let's look at an example where we might round to 3 significant digits. And let's suppose we have more numbers available. So let's say we have 12,345, 1, 2, 3, 4, 5. And we're interested in expressing this with 3 significant digits. So again, we begin counting from the left. So the first 2 are just going to be 1, 2. And now the third digit is a 3, and the one after it is a 4. So 4, according to our rounding convention, tells us to go down. So we're going to keep the 3 as it is. And then our second rule tells us to make sure we keep those placeholders. So we're going to add those final 2 zeros. So 12,345, when expressed to 3 significant digits, is going to give us 12,300. Now, there are some particular cases where we actually count the zeros as one of our significant digits. And this will happen when the 0 is sandwiched between other numbers. So if we look at another example, and let's suppose this time I'm working with 1042, and we want to write this number to 3 significant digits. So we proceed exactly as we have in the earlier examples. We are going to keep the 1, our first digit from the left that's non-zero. We then keep the 0, so the 0 is now playing an important role by maintaining that placeholder value. And then our third digit is a 4, the one after it is a 2, the 2 tells us to round down, so we keep the 4, and then we add the 0. So this is our first example we've seen in this section where one of the final significant digits is in fact a 0. But it's important because it's in between the 1 and the 4, so you can sometimes have zeros that play the role of being significant. And I've got one more example of this with a very famous number that some of you may recognize. So we're going to look at a rather large number, 299,792,458. And we're going to try and write this number using 3 significant digits. So of course we have a lot more than 3 digits, but we're going to try and simplify it a little bit. So we begin by considering the first couple of digits. So we've got a 2, next along we have a 9, our third digit is a 9, and then we would normally look at the next one along, so the 7 here. Now the 7 is telling us to round up. So that third 9 needs to go up. But if we go up from 299, the next number is actually going to be 300. So what we see here is writing this to 3 significant digits. Following those rounding conventions, we actually have to go up to 300 million, which is, of course, the exact same value were we to write this same number using just 1 significant digit. But here, because we're working with 3, those 2 zeros at the end, 300, they are significant. They are playing an important role according to the convention. So we can do the same and follow the same rules for decimals, for decimal expansions. So let's begin with a number 0.136. And again, let's look at rounding this number to 3. Well, not 3, we've already got 3, haven't we? Let's do 2 significant digits. Okay, so we want to round or write 0.136 to 2 significant digits. So again, we follow the same conventions. So the first non-zero number from the left means the 1. So we have to keep the 0 point. We have to keep that for the placeholder value. That's telling us where we are in the number system. So we have to keep that. And then we're going to get a 1. And then we've got 3, 6. So the 3 followed by the 6. The 6 tells us to round up. So we're going to get the 4. So we'll look at one more example, again with the decimals. So let's suppose we have a slightly longer number. So let's have 0.00119887. And again, suppose that we're writing this to 2 significant digits. So again, we follow the rules, starting from the left. So we have to keep the placeholder values. So that's going to be 0.00. We then want to start counting the significant digits. So we've got a 1. And then the next one along, because we're interested in 2 significant digits, we've got a 1 followed by a 9. So the 9 is telling us to round up. So that's going to give us a 2. And you'll notice we're kind of just ignoring all of those numbers at the end because they're not actually adding any value. They don't tell us anything about the placeholder values of the decimal. So there you have it. That is many, many examples of both large, small numbers, decimals, non-decimals when working with significant digits. And the important thing to remember is to follow our OK. Sorry, I'll just pick up on, so there you have it.
Sounds good.
OK. So there you have it. We've looked at lots of different examples of large and small numbers and how we write them using different amounts of significant digits. And the key to it all is just remembering our 3 important rules, which, as a quick reminder, are shown on the screen. We start counting from the left, the first non-zero digit from the left. We have to remember to keep all the placeholders. And of course, don't forget those rounding conventions. recall that the rational numbers are defined as fractions, where we have one integer on the top divided by another integer. So if we're going to be able to understand and work with the rational numbers, we need to know how to work with fractions. So one of the first things that we might do with a fraction is to simplify it. So in order to simplify a fraction, there are two key pieces of information or two key rules that we need to make sure we are familiar with. So the first of those rules is that if we have a fraction and we multiply or divide the top and the bottom by the same number, then the value of that fraction does not change. So if we look at an example, if we have the fraction a half, and I take the half and I multiply by 3 on the top and 3 on the bottom, and as you can see here, 3 over 3 is just 1, which is why this doesn't change the value. But we can see doing that multiplication, 1 times 3 over 2 times 3 gives us 3 over 6. And so in fact, these two fractions, a half and 3 divided by 6, are going to be the same. We would say they are equivalent fractions. Now, what we're interested in is what if we start from something like 3 over 6 and we want to reduce it down or simplify it to the simplest form, which here would be the half. And in order to do that, we need our second rule, or our second key piece of information, which is related to what we call prime numbers. Now, recall, I hope, that a prime number is a number which has only itself and 1 as factors. So it's a whole number, it's a positive integer, and the only numbers that will perfectly go into that number, perfectly divide it, are those which are itself and 1. So for example, 3 is a prime number. The only way to make the number 3 is 3 multiplied by 1. But 6 would not be a prime number. So we can make 6 by doing 6 multiplied by 1, but it also has other factors. So here, as example, 6 is 3 multiplied by 2, so it has other factors than just 1 in itself, so therefore 6 is not a prime number. So we're going to use now the prime number definition and prime factors to simplify some fractions. So our first example is going to be the following. We will look at 9 divided by 12. So this is a rational number, this is a fraction, 9 on the top, 12 on the bottom. And the way we might approach this is to think about how do we break down both the number 9 and the number 12 into some of those factors. So 9 is, of course, 3 multiplied by 3. So what I would recommend doing is just beginning by writing that out, and then we'll come to cancellation in a moment. So 3 multiplied by 3 is definitely equal to 9. And then with 12, we've actually got a few choices here. So 12 has several different factors. But given what we've already done on the top, I'm going to write 12 as 3 multiplied by 4. So by doing this, what we're beginning to do is to break down the original numbers into those smaller pieces. They're not all prime, but we have a good number of prime numbers in there, which is going to help us. So now that we have 2 3s on the top and a 3 and a 4 on the bottom, we can then cancel 2 of those 3s. So this 3 is going to cancel with this one, for example, and what we're left with then is 3 divided by 4. Now, we could, of course, stop here, but in fact, you want to sort of take a moment to check that you're happy that this is indeed the simplest form of the number. And it turns out it will be, because the 3 on the top is a prime number. So even though the 4 on the bottom can be broken down into 2 multiplied by 2, that's not going to help us, because the number on the top, the 3, cannot be broken down, precisely because it fulfills that definition of being a prime number. Okay, let's look at a slightly more advanced example now, and let's look at 28 divided by 42. So again, we begin by thinking about which numbers can we break down, the numerator on top and the denominator on the bottom. What factors do they have? So here, again, there's a few different ways to do this, but I'm going to start reasonably straightforward and use the fact that they're both even numbers. So they're both even numbers, which means they have a factor of 2 in both the top and the bottom. So 28 is 2 multiplied by 14, and the 42 is going to be 2 multiplied by 21. Now again, this allows me to cancel the 2's. So we've turned this now, and I'll write this out nice and clearly, so we can say this is equal to 14 divided by 21. Now, neither of these numbers are prime, but sort of we want to think about what their factors might be, so we can then check that to see if we can reduce this further. So 14, famously, is 2 times 7, if you remember your 7 times table, and 21 is also in there in the 7 times table and is 3 multiplied by 7. So once we've now broken both of those down, we can again cancel that 7, and this is going to leave us with 2 divided by 3. This time both the number on top 2 and the one on the bottom 3, both of them are actually prime numbers. So again, this is going to be our final fully reduced or most simplified form of the initial fraction 28 divided by 42. Okay. Now, as well as simplifying fractions, I mentioned at the beginning we want to also be able to manipulate them and work with them. And so what that is going to mean is if we're given 2, 3, some number of fractions, we want to be clear about how we combine them. So for example, how do we multiply fractions, how do we divide fractions, and how do we add fractions? So we'll look through some examples with numbers. But then what I'm going to focus on here is actually, can we come up with the general rules? So no matter what numbers, whatever fractions we're given, can we come up with a rule or an equation that's actually going to give us the output? So if we first think about multiplying fractions. So to multiply 2 fractions, it's probably the easiest one of the lot. We just take the numbers on the top, multiply them together, take the numbers on the bottom, multiply them together. So if we look at an example, 1/2 multiplied by 3/4, we multiply the 1 and the 3 on the top, which gives us 3, and on the bottom we do 2 times 4. So the numbers on the top stick together, get multiplied, ones on the bottom stick together, get multiplied, gives us the answer 3 divided by 8. So what does that look like now for any possible pair of fractions? So rather than just saying we're working with the specific values of the 1/2 and 3/4, what if we have any pair of fractions? So any fraction or any rational number has a number on the top, I'm going to call A, and a number on the bottom, let's call it B. And then when I multiply that by another rational number, another fraction, let's say that one is C divided by D. So if we follow the rule or follow the example that we just did, it says we just multiply the 2 numbers on the top, so that's just A times C, and then on the bottom we multiply B and D, so we get BD. So again, we can check this with our concrete example. We did 1/2 times 3/4, so if we think about what this means, this is telling us that A is 1, B is 2, C is 3, D is 4. And when we multiply those together, we get A times C on the top, which is 3, and B times D on the bottom, which is 8. Now, the reason it's helpful to think about these rules and this approach using variables, using these letters to represent the numbers, is now it doesn't matter what fractions I'm working with. And this is exactly the kind of concept, the kind of ideas that you use when you're programming, when you're working in computer science, because you don't know what numbers you're going to be working with, so you want to have a general approach to putting all of that together. Okay, so that is multiplication. So now let's think about division, the opposite. So if we want to divide 2 fractions or divide a number by a fraction, then we actually use multiplication to help us do that, because we now have a way of doing multiplication for any pair of fractions. So to divide a fraction, what we do is we just multiply by what is called the reciprocal. So the reciprocal is just a fancy word that we use to mean flip the fraction over. So best, I would say, seen through an example. So if I want to take 1/2 and I want to divide by 1/3, I want to divide 1/2 by 1/3. So the reciprocal says flip the fraction. So we're dividing by a third, so the reciprocal is going to be 3 over 1, and we multiply by the flipped fraction. So a half divided by 1/3 is just a half multiplied by the fraction upside down, 3 over 1. So again, we've got 1 times 3 on the top, 2 times 1 on the bottom. We just talked about how to do the multiplications, and we get the answer there of 3 divided by 2. So like before, let's now generalize that for any pair of fractions. So again, we will work with a over b and c over d. So if I have the fraction a divided by b, and I want to divide that by c over d, then following the rule that we've just described, we know that that's the same, or the way to work it out, is a over b multiplied by the upside down fraction. So that's going to mean d on the top and c on the bottom. And now we just follow the rule of multiplication and say that we get a times d divided by b times c. And exactly as with the multiplication formula, we could substitute in the numbers that we just used, but this will always give us the correct way to divide one fraction by another. Now the final one that we're missing, we've done multiplication, we've done division, all that's left is addition. So how do we add fractions? Often when working with, let's say, whole numbers or integers, addition is like the easiest one. It's one of the first ones that we learn when we're young. But with fractions, it's probably actually the most difficult. There's a little bit more to it. And it comes down to this important rule about adding and subtracting fractions. You can only do it if they have the same denominator. So that number on the bottom must be the same if you're going to add or subtract fractions. And we've already looked at how to change the number on the denominator. We talked about simplifying those fractions and the fact that as long as we do the same to the top and the bottom, the value doesn't change. So that's really going to help us to understand what's happening here. So let's look at another example. So I want to add a half and 1/3. They currently do not have the same denominator. This one has a 2 on the bottom, this one has a 3. So we need to turn them into a number that has the same denominator, and then we can do that addition. Now what we've learnt so far is that the value doesn't change as long as we do the same to the top and the bottom. And similarly, we've got a 3rd and we do the same to the top and the bottom. Now you might be wondering, well, how did you know what number to multiply on the top and the bottom? And what we're doing there is we're finding what's called a common denominator between the two numbers. Now there are a few different ways to do this, but in terms of a foolproof method that will always work is I want to add a half and a 3rd. So I take the first number, which here is a half, and I'm just going to multiply on the top and the bottom by the denominator of the second number. So because I want to add a 3rd, what that's telling me to do, and again this will always work, I can just put a 3 on the top and a 3 on the bottom, and what I'm going to end up with is going to be the same denominator for both of them. So I do the same for the second one. So it's the 3rd, and I want to add a half, so that's telling me to put a 2 on the top and a 2 on the bottom. So splitting it up like this, we can see very clearly we're not changing these numbers. We're multiplying by 3 over 3, which is 1. We're multiplying by 2 over 2, which is 1. But now we can use our rules about multiplying fractions. So this first bracket is going to be 1 times 3 over 2 times 3, as written here. The second bracket is going to be 1 times 2 over 3 times 2, as written here. And then they're going to turn into 3 divided by 6. This one will turn into 2 divided by 6. And now finally, we have two fractions with the same denominator, the same number on the bottom. We can add them. And you'll notice here, importantly, the number on the bottom doesn't change. We just add the numbers on top. So as I said, there's a lot more to addition of fractions, and it does rely on knowing the fact that fractions don't change value when you do the same to top and the bottom, and relies on knowing how to multiply them. So as a final thing for this section, let's see if we can come up with a general formula of how to do this for any two fractions. And once again, I'm going to go over to the board. So we will begin with the same two general fractions. So we have a divided by b, and we want to add this to c divided by d. And once again, the example we just saw, we had a half plus a third, so we could work out a, b, c, and d accordingly. Now what we did with the half and third example was we multiplied the top and the bottom by the other denominator. So if we focus on the first one, if we focus on a over b, now I want to multiply that entire fraction on the top and the bottom by the denominator, by the bottom of the second one. Right? In our half and third example, we took the half, multiplied the top and the bottom by 3, because the 3 was on the bottom of the third. So if I follow that rule here, then we can say this is a divided by b, and then I want to multiply by the second denominator, which is d, but I have to do it on the top and the bottom so that I don't change the value of the fraction. And then we do the same thing for our second fraction, c over d. So we start with c over d, and as before, we have to multiply by the denominator, the bottom of the other fraction. So here that's b. So that's going to be b divided by b. Now we can do the actual multiplication. We talked about how to do that. So that gives us AD divided by BD plus C times B. So CB divided by B times D on the bottom. And you'll now notice both of them have the same number on the bottom, the same denominator, so now we can add them. So the general formula there is going to be AD plus CB divided by BD. So no matter the two fractions we start with, if we can work out what is A, B, C, and D for our pair of fractions, the answer will always follow and fit into this particular formula. So to summarize, we wanted to talk about fractions because they are how we represent rational numbers. And if we want to be able to work with rational numbers, we would like to know when they are the same. So that comes to the when fractions are equivalent, how to simplify or reduce a fraction. We also then looked at how we might multiply fractions or rationals, how we might divide them, and how we might add them. When given the decimal expansion of a number, how do we know if it is a rational number and can be written as a fraction, or whether it cannot be written as a fraction and therefore is an irrational number? We need a way to be able to convert a decimal number into a fraction. And it's not as easy as it seems to spot when you can and cannot do this. Now, to emphasize this, I have some examples on the screen of common fractions and their representative decimal expansions. You hopefully recognize a good number of these. So a half, 0.5. A third, 0.33333, continuing forever, as demonstrated or signified by the ... A quarter, 0.25. So we're back to ending. This is a terminating decimal as it stops. A fifth, 0.2, also pretty short. But then suddenly a sixth, we've got 0.1666666. 6 is again continuing forever. And we have plenty of others on the other side of the screen. Now, all of these are indeed rational numbers. So if you were given some of these decimals, if I gave you 0.25, it's likely you would recognize it and know that it was a fraction, it was a rational number. But if you were given some of the other numbers here, or any general decimal expansion, we would like to know, can we identify when you can turn it into a fraction, and therefore it's a rational number, or when you cannot do that, and then it's going to be an irrational number. So what we're going to look at now is how you can turn decimals into fractions and when that is going to be possible. So we'll begin with a few examples. So if I have a nice short terminating decimal, let's suppose it's 0.123, and it stops. So 3 decimal places, we've got there the tenths, hundredths, thousandths. Now if I wanted to turn this into a fraction, the way we can do this is by using those placeholders. So using the tenths, hundredths, thousandths, and using powers of 10 to shift the decimal place across. So the way I like to set this up is if we call this number, the one we want to work out, let's suppose this is x, then what we want to think about is if I now do 1,000 lots of x, then what I'm going to get. We want to think about what does that do. So 1,000 is 3 lots of 10. It's 10 times 10 to get 100 times another 10 for the 1,000. And each 10 that's in there is shifting the decimal place 1 position to the right. So here it's going to shift it 3 positions to the right. So 1,000 times 0.123, we go 1, 2, 3, and we get the answer 1, 2, 3, in fact. So now we know x was the number we were working with. That was our decimal expansion. We know what happens when we multiply it by 1,000. We just shift it across the decimal place. But this means now if we divide both sides by that 1,000, and this is going to give us our rational number, it's going to give us our fraction, we say that x is just 123 divided by 1,000. And this now satisfies our definition of being a fraction, of being a rational number. We have an integer on the top, and we have an integer on the bottom. OK, so let's look at another one. Suppose now I have 0.0625. So again, this is a terminating decimal expansion. This is stopping after 4 places. And those 4 places are going to help us when working out what to multiply by. So because it's 4 places, if I call this x, what we want to think about now is 10 multiplied by itself 4 times. So that's going to give us 10,000. So 10,000 lots of x is going to equal, we're going to shift the decimal place 4 places across. So that's actually going to give us 625. There is, of course, a 0 in front of that 6, but we don't read that when we write numbers this way. So we know that 10,000x is 625. So that's going to tell us now that x is just, again, divide through by that 10,000 is 625 divided by 10,000. Now, possibly, we could simplify this. And perhaps we could have simplified the first one. It turns out you can't. The 123 on top is prime. But this one we can simplify. We can reduce this down to a simpler fraction. And the way we might do this is by thinking about perhaps factors of 5. So if we begin by pulling out a factor of 5 on the top and the bottom, then we can say, well, this is the same as 5 times 125 divided by 5 times 2,000. So you'll notice 5 times 125 still gives me 625, and 5 times 2,000 still gives me the 10,000. But of course, we can now cancel those 5s on the top and the bottom. So we've reduced the fraction a little bit. But it looks like we can also take out another factor of 5. So let's do that. So we're going to now get 5 lots of 25, give us the number on the top. And then on the bottom, 2,000, that's going to be 5 times 400. So again, we can cancel the 5 on the top and the bottom. Looks like we can do another factor of 5. So I'm just going to clear this and write that again at the top. So 25 over 400 was where we got to. So that's now going to be 5 times 5 divided by how many 5s go into 400? It's going to be 5 times 80. Again, we can cancel the 5 from the top and the bottom. So now we're working with 5/80ths. But again, we can actually pull out another 5. So 5 over 80 is actually the same as 5 times 1, to make that very explicit, over 5 times 16. And so again, we cancel that final 5, and the decimal we started with was 1/16. And just to make that very clear, what we've shown here is that 1/16 as a rational or a fraction is actually written in decimal form as 0.0625, which of course was not immediately obvious in any way when we started, which is why it's important to be able to convert from any given decimal, to have a method to follow to be able to turn it into a fraction. So both of those examples we've looked at were terminating decimals. So they stopped after some number of places. Now, of course, when I showed the examples on the screen, we also had some numbers there that didn't, that went on forever. They were non-terminating decimals. And we saw that quite a few of them actually had some repeats. So one of those numbers that we saw was the following. We had 0.111 ... carrying on forever, which is also sometimes written as 0.1 with a bar over the top to indicate that the 1 is repeated. Now, we're going to try and use the same method to write this number as a fraction. So as before, we start by saying this is going to be x. And again, the reason we do this is because we're going to multiply it by some power of 10 and then do some clever manipulation. So here, I think we only actually need, because the repeated position or the repeated digit begins in that first position, we actually only need to shift it over one position. So if I multiply this by 10, let's think about what happens. So 10x tells us to shift the decimal place one position to the right. So that's going to give me 1 point and then 1, 1, 1, ... If I want to use the bar notation, that would be 1.1 repeated with the bar again over that 1. Now, at this point, it's still a decimal, but this is the clever part. So we have an expression for 10x, 10 times our number, and we also have an expression for the original number. So what we do is we subtract those two numbers. So if I do 10 lots of x, and then I subtract x, so we know that that is equal to 9 lots of x. But we also have two expressions for, we have an expression for 10x, we have an expression for x. We have those two expressions. So this is the same as saying, well, if I write out the expression for 10 lots of x, that's 1.111 ... And then we've taken away the original x, which is 0.111, carrying on. So what we're seeing here is actually everything after the decimal point is going to perfectly cancel. So when we take away that repeating 1, even though it goes on forever, it goes on forever in both numbers. So they're all going to cancel each other out. So when we do this, we just are left with 1. So what we've got is that 9 times x equals 1. So if we divide both sides by 9, then what we've got here is our original decimal with the repeated 1 is 1/9. Now some of you may have spotted this when I wrote it at the very top of the board because I did show it on the slide earlier. But we've gone through here the calculation of how we can convert that repeating decimal into a fraction. Now we'll look at one more example of a slightly longer repeating decimal. And this one will be 0. I have to remember all of these digits. 1, 4, 2, 8, 5, 7, and then that is going to be repeated. So kind of imagine like copying and pasting those 6 digits one after the other forever. So we'll start as before by labeling this as x. Now, because we have 6 digits that are going to be repeated, those 6 positions, we actually need to shift the decimal place 6 positions to the right. So that's telling us to multiply 10, 10, 10, 10, 10, 10, 6 times. So 10 to the 6, using the scientific notation or the exponent. So that means that doing that, we get 1 million x. So multiplying by 1 million, which again is going to shift the decimal position 6 places. 1 million x is equal to 142,857. And then remember, those 6 digits just repeat. So then 0.142857. And then there would be another one, and another one, and another one. So that again, that bit we can write with a bar over the top to show that it's repeating. Now, we follow exactly what we've done with the previous example when we worked out 1/9. So we simply subtract x from both sides of this equation. So we've got 1 million x, take away 1x gives us 999,999x. And then what we're doing on the other side is we have the 142,857 point repeated decimal, take away 0 point repeated decimal. So just to really spell that out, we have the 142,857 point, this whole repeated section, and then we're subtracting, so that was the million lots of x, and we subtract, take away 1 lot of x, which is 0.142857 with the bar. So just as before, everything after the decimal place is fully cancelled out. So we lose all of that, and we can therefore say that this is equal to 142,857. So now we divide both sides by 999,999, and the original decimal expansion that we started with is equal to 142,857 divided by 999,999. And now we begin the very long process of trying to simplify this particular fraction. I will not go through all of those steps because there are many, but you can simplify. You can pull out those common factors from the top and the bottom, and you'll have to just take my word for it at this point. That will turn into 1 divided by 7. So it's actually one of the numbers again that we had on the screen at the very beginning. Now, we've seen there examples of terminating decimals, decimals that stopped, and how to turn those into fractions. So that means they are rational numbers. We saw an example of a repeating decimal, which we were also able to turn into a fraction and a rational number. So it turns out that if we have a decimal expansion that does not repeat, that is actually going to be our definition of an irrational number. So that gives us an answer to the original question I asked right at the very beginning of this section, where I said, how do we know if the number is rational or irrational? So the summary is that given a specific decimal expansion, given a decimal number, If we can turn it into a fraction, it is rational. And we can do that provided the decimal expansion terminates, so it ends at some point, or when it repeats. So there are some number of digits that are then copy-pasted forevermore. If neither of those things are true, then we say the number is irrational. Oh, sorry. Could you just put the green lights on? Apologies. Just saw that then. Thank you. OK. There are many different types of number, and there are various relationships between them. Now, to keep track of how the naturals are related to the integers and the rationals, the irrationals, the reals, I've come up with a helpful concept of trying to visualize the relationships, and I'm going to do this using some colored rope. Bear with me. So we will begin with the first, let's say, simplest set of numbers, collection of numbers, the natural numbers, the ones that we use to count. So we'll have those as our starting point, represented here as this yellow rope, this collection. And we might put 0 in there, including this as a natural number, remember, and also 1 as well. So 2, 3, carrying on could also go into that same collection. Now, from the natural numbers, we then build up to get the integers. So rather than just relying on positive numbers, we bring in the negatives. And so we can then say, well, anything that is a positive whole number, one of our positive integers here, our natural numbers, that's also part of the integers, but we have more. So we can represent that by adding in an additional hoop, let's say, or an additional collection here in pink, which is going to represent those integers. So again, the integers contain the natural numbers. Anything that's a natural number is also an integer, but we also get other numbers. We get the negatives. So things like -3 and maybe -42 would go into that integer collection, but they're not inside the collection of natural numbers. Now from here, we then build up from the integers to get the rational numbers. So the rational numbers are our fractions, where we have an integer on the top and an integer on the bottom. So as the name suggests, or the definition suggests, they are built from the integers. And anything that is an integer is a rational. You just put a 1 on the denominator. So that's going to mean that this relationship now is we can extend even further to our purple rope, which is going to represent those rational numbers. Okay, it's getting crowded. So anything that's an integer is a rational, which is why it encloses that collection. But then we have other numbers, so for example, 1/2 and 22/7. They are rational numbers, so they're outside the integers but inside the rationals. We then have the irrationals. Now the irrationals are entirely separate. So the irrational numbers, by their very definition, are those numbers that cannot be written as fractions. So they're going to be an entirely separate group of numbers over here. So this red collection, this red hoop, is going to represent, make sure they're not touching each other, that's going to now represent our irrational numbers, which again are those things that cannot be written as fractions, so they are very much outside of this other large collection. So that could be something like the square root of 2, which cannot be written as a fraction. That's one of those never-ending decimals, or perhaps something like pi. And now we then have a final collection of numbers that I'd like to display with this much longer rope. And this is going to kind of encompass both the rationals and the irrationals. So what we're going to see here is the real numbers, which again we define to be both the rationals and the irrationals. This needs to go around everything. So let's see if I can manage this. So we go all the way around the purple one, all the way around the red one for the irrationals. Okay, there we go. That's better than anticipated. All the way around this way, and kind of join that back up over here. So this white ring is actually representing now the real numbers. So again, the real numbers, which is going to mean anything on the number line, any number you can think of, is going to contain both the rationals and the irrationals. Now, in this visualization, we do have a little gap sort of here. So sort of something suggests we could have something that's not a rational, not an irrational, but is inside the reals. And it turns out that this space is actually completely empty. If you have a real number, it must be somewhere inside the purple section, the rationals, or somewhere inside the red section, the irrationals. So if I attempt to demonstrate this, it would more accurately, we should really be pulling this tight up against both the purple and the red, because there simply isn't space, there is no number that goes in between both the rationals and the irrationals. So there we go. So again, there's no space now for anything to be in there. We've got the reals, which is combining, enclosing all of the rationals, all of the irrationals, and then inside the rationals, inside the purple, we've then got the integers and the natural numbers. Now we've almost finished. I just think, you know, as good as this pi symbol looks, it doesn't quite look as good, or certainly doesn't look as tasty as an actual pi. So I think, just to round this off very nicely, a much better representation of our number pi there with this lovely circular pi. Now, whilst these are the base collections of numbers that you want to recognize, that you want to be familiar with and know how to work with, there are other classifications. But as we can see, this is already getting quite busy on my demo table. So I'm just going to pop over to the screen just to add in some of my other favorite collections of numbers. So as a recap of where we are from the ropes on the table, we've got the naturals, counting numbers inside the integers, where we bring in the negatives, inside the rationals, which are our fractions. We have those numbers that aren't rational, cannot be written as fractions. There are irrationals over here, and then the reals are those two things together. Now, the next collection of numbers we can add to this is something called a constructible number. Now, this goes back to the time of ancient Greece and the geometers working around that period, and they were playing around with sort of constructions and whether you could create a number using only a straight edge, which we would refer to as a ruler, and a compass, so the device for drawing circles. And anything that which you can do this for, we call a constructible number. You can construct it geometrically. So an example of a constructible number would be something like the square root of 2. And this is a really nice example here because of where this fits now on our visualization. So we have all of the original ones in white with the irrationals there in red, and the constructibles contain anything that is rational, so all of those ones, but they also overlap and go into the irrational numbers. So the example I just mentioned, the square root of 2, it's an irrational number. It has a never-ending, non-repeating decimal expansion. Cannot be written as a fraction, but you can construct it using a compass and a straight edge. So it sits in this little region here. Now the next one, going up further, we get to something called the algebraic numbers. So the algebraic numbers are defined as the roots or the solutions to a polynomial equation where all of the coefficients in that equation are integers or rational numbers themselves. So an example of an algebraic number would be something like the cube root of 2, where we write that, we use the square root sign, but we put a 3 there to indicate that it's the third root, the cube root. And this particular number can be found by solving the equation, the algebraic or polynomial equation x cubed equals 2, so we call it an algebraic number. And it turns out that the cube root of 2, as well as being algebraic, is not constructible. It's actually a very famous problem called doubling the cube, which the Greeks tried to solve for many, many years and was actually shown to be impossible in some point in the 1800s, so a long time later. So what that means for our diagram is the algebraic numbers contain the constructibles, so the green hoop is outside all of the yellow and all of the other white ones, but we also have a little space here where we can put something like the cube root of 2. It's the solution of an equation, but you cannot draw it using a straight edge and a compass. Now the next section, if we go outside of algebraic, there's only a couple more, the next one is called the transcendental numbers, and these are just defined as all numbers that are not algebraic, so anything outside of that green circle, anything outside there is transcendental. And remember This space here is actually empty. So the transcendentals are going to be irrational numbers over here. But I prefer a slightly different subdivision of this final category. And that's because it comes from a mathematician close to my own heart as a fellow Brit, Alan Turing. So in 1936, he defined what we call the computable numbers. And he said that a computable number is any real number that can be computed to any desired precision by a finite terminating algorithm, which I think is a really nice example of the intersection there between maths and computer science. So a computable number is something we can compute, and we have various algorithms, famous algorithms for doing this for specific numbers. The number pi, one of the most famous irrational numbers, can actually be calculated to as many decimal places as we want using something called Chudnovsky's algorithm. Now, the current world record is 314 trillion decimal places of pi. We could get more. It would just take even longer to run. It took 110 days to get 314 trillion decimal places. And in case you were wondering, the final place that we know, it continues forever, but the last digit we know is currently an 8. But watch this space, because there are more to be uncovered. But what this all means is we have the computables outside of the algebraic numbers in the blue, and a number like pi is not algebraic, so it's going to pop in there. So as we can see, there is a whole lot of different relationships and different ways of classifying numbers. The most important ones you want to be comfortable with and aware of are going to be those initial ones, the naturals, the integers, the rationals, and the reals, plus the irrationals. But as you can see, there are a whole host of other ways of defining a number. there are many different types of number: naturals, integers, rationals, reals, irrationals, and there is a whole host of relationships between them, how they relate to one another. So what we're going to try and do, and I'm going to try and do, is to visualize this number collections. Sorry, let me just start that again.
Can I mention one thing?
Yep.
Don't know if it's different in Britain, but if you're comparing multiple things, you would say among these numbers, not between.
Relationships among. Okay, yeah.
Between is two, among is.
I'll just say many different. Okay, yeah, cool, yeah, fine. No, that's just a me thing. That's definitely a me thing. Okay, yeah. I'll avoid saying either word. All right, sorry, let's go again. Cool, right, okay. I'm going to say, right, there are many different numbers, many relationships, different numbers, which are linked in various different. Okay, right, cool.
You can restart anytime, Tom.
Okay, thank you. Okay. There are many different types of number which have a range of different links between them. So we have the naturals, the integers, the rationals, the irrationals, the reals, often one collection built from some of the earlier ones. So what I'm going to try and do is to visualize those relationships using colored rope. Bear with me. So we begin with the natural numbers, the counting numbers. And this is going to be represented as a yellow ring, let's say, over here. And this will contain the numbers we are used to, most familiar with, let's say 0, and also perhaps 1, 2, 3, etc. Now, from the counting numbers, we then bring in the negatives. So for the integers, we take those positive natural numbers, or the counting numbers, and we bring in the negative versions. So the integers contain the natural numbers. And we're going to represent that by adding a ring around those natural numbers, because anything that's an integer or anything that's a natural number is also an integer, so it's very much inside that same collection, but also we have things that are added. So if we take something like -3, a negative number, that's going to sit outside of the naturals, but it's definitely still inside the integers. And here's another example, perhaps of -42. Now, from the integers, we then go on to define the rationals. And the rationals are our fractions. Now, our fractions are a ratio where we have a single integer on top divided by another integer. So that means that anything that's an integer is also a rational. So the rationals are going to actually form an even bigger collection of numbers, which we'll show with this purple rope coming all the way around the integers. So anything that's an integer, again, -3 is our example here. If I just put -3 divided by 1, now it's a rational. So anything that's an integer is inside the collection of rationals, but we also get some extra stuff. So we've got a half, or we've got something like 22 divided by 7. Now from the rationals, we then move on to the irrationals. Now the irrationals are their own completely different, separate collection of numbers. We actually define them to be exactly not a rational number. So an irrational is something that cannot be written as a fraction, meaning it's not a rational number. So this needs to go over here, completely separate, to represent those irrational numbers. So the irrational numbers could be something like the square root of 2, which is a never-ending, non-repeating decimal expansion, making it an irrational number, or perhaps the most famous irrational number, the number pi, which talks about the geometry of circles. So now we've got the rationals containing some other stuff with the purple ring, and we've got the red one for the irrationals. Now I have a final rope left, and this is going to actually encompass everything that's on the table. So this white rope, let's see if I can get this all in position, a bit longer than the others. So this white one is going to enclose everything that we've got, both the rationals and the irrationals, and this is going to represent the real numbers. So we go all the way around the edge, all the way over here to represent the real numbers. So the real numbers are made up of both the rationals and the irrationals. Now, there's an interesting thing to observe with this visualization, and that is this kind of space between the white, so it's definitely something that's a real number, but is not a rational and not an irrational. And actually nothing goes in here. So what we really should do is kind of close up this rope. Because if I take any number, any point on a number line, it has to be a rational or an irrational. There is nothing else that that number can be. So just to really stress that point, what's happening here is this real number boundary should actually be right up against both the rationals and the irrationals. So there's no space between them. Anything that's real must either go in the irrational space over here or go somewhere inside the rational, could go inside the integer, could go inside the natural, but it's got to be somewhere in there. There is no gap between the white and the other colored ropes. So we're almost done, but I have to be honest, I'm not entirely convinced with this particular representation of pi. It certainly could look a little more tasty, shall we say, but fortunately I've got just the prop we need. So now we have a very beautiful, clear and tasty representation of all of these different classifications of numbers. So these are the core classifications, the core groups of numbers that you want to recognize, you want to be familiar with. So the naturals going into the integers, going into the rationals, the irrationals, and those two together being the reals. But there are many other types of number and many other classifications that exist. So the table's probably a little bit busy already, so I'm going to move over to the screen to show you some of my favorites. So just to kind of recap and reframe what we have on the table, we've got naturals, integers, rationals, irrationals over here, and the reals containing everything. So the next kind of collection that I particularly enjoy thinking about is something called the constructible numbers. So the constructible numbers are defined through geometry, and these were a favorite of mathematicians and scientists in ancient Greece. And they were any number that you could construct, hence the name, using a compass, the device for drawing a circle, and a straight edge, which we would refer to as a ruler today. So using a compass and straight edge, if you can construct that number, or construct a segment of a line of that number's length, then we call it a constructible number. The name gives away the definition. So an example might be the square root of 2. So we can construct the square root of 2 by drawing a unit square and putting a diagonal across it. So the square root of 2 is constructible. And it turns out that the constructibles kind of sit at this lovely overlap between the rationals and everything over here and the irrationals in this red hoop. So the constructibles contain everything that's rational plus some of the irrationals. So for example, the square root of 2 is very much an irrational number, but it's also constructible. You can make it geometrically. The next collection, kind of going one further set out, we come to is the algebraic numbers. Now the algebraic numbers are numbers that you can define or find by solving a polynomial equation where the numbers in your polynomial are integers or rationals. So for an example here, we have something like the cube root of 2, where we write this using the square root, but we put a 3 over the tick to emphasize that it's the cube, the third root of the number. And this is actually the solution of x cubed equals 2. It satisfies this equation. And it's actually a famous problem that the ancient Greeks used to try to work on, called doubling the cube. And it was shown several thousand years later that it was impossible to double the cube, because that problem is the same as trying to construct the cube root of 2. So what that means is the algebraic numbers contain everything that's constructible, but also some other stuff. And so the cube root of 2 is not constructible. You cannot double the cube, and sits nicely in that gap. Now, anything outside of the green line has a whole name, a whole collection, which we refer to as the transcendental numbers. So if you are not algebraic, you are transcendental. However, I'm going to introduce a sort of subcategory of the transcendental numbers, which I couldn't resist talking about because it's actually named or was discovered created, invented, whichever word you prefer, by the British mathematician, a fellow Brit, Alan Turing in 1936. But before we get to that, the transcendentals are just going to sit nicely here, as I say, outside of the algebraic numbers. But, as mentioned, the transcendentals can be subdivided. And what Alan Turing did was he actually said, well, what we have here really are computable numbers and non-computable numbers. So the definition he uses is that a computable number is something that can be computed to a desired precision through a finite terminating algorithm. So this is a really nice link between maths and computer science. Alan Turing, of course, working in both fields back in the 1930s and 40s. And it also now allows us to put an extra circle on our already quite busy diagram. So an example here would be something like pi. Again, we've seen already a nice tasty irrational number. And pi can actually be calculated to as many decimal places as we want using a range of different algorithms, one of the most famous being something called Chernovsky's algorithm. We now actually know the world record for pi is knowing it or being able to compute it to 314 trillion decimal places. We could know more, but it would just require even longer to compute. So it took 110 days to get all of those decimal places. And the 314 trillionth digit is in fact 8, in case you were wondering. But what that all means on our diagram is the computable numbers contain everything else, and we have a number like pi popped in here. So, as you can see from the very, very busy diagram, both on the table and on the screen, there are a whole host of different types of number. You can continue down this rabbit hole as far as you want, but just to really emphasize for you all watching, the key ones that you really do need to know and want to be comfortable and familiar working with are going to be those naturals, those integers, those rationals, the irrationals, and the reals. In this chapter, we've heard about at least 9 different types of number. We started with the most familiar, the counting numbers. We then brought in the negatives and built the integers. We combined the integers to get the rationals. And then throwing in the irrationals, we saw how that gave us the reals. We also explored decimal expansions, when they could be terminating or non-terminating, when it is and isn't possible to turn a decimal into a fraction. And we also identified how we can use that to work out whether a given decimal is rational or irrational. And we finished with a lovely visualization of all of the relationships among these different collections of numbers and a little throw forwards to some more advanced classifications. What we would like to do next is talk further about these relationships, but that's going to require some new terminology in the form of sets. Fortunately, that's exactly what we're doing in Chapter 2.